In this video, we're going to be looking at two-dimensional motion and lots of free response questions from previous Calculus BC exams. Now, in the first semester, we looked at rectilinear motion, which was motion along a line, usually the x-axis or the y-axis or something like that. And so we had some position function, which we, usually called maybe like x of t or y of t. Some people might call that s of t. I wasn't a huge fan of that, but velocity, okay, we knew that velocity was the derivative of position. We knew that acceleration is the derivative of velocity, which is also going to be the second derivative of position. We found speed by taking the absolute value of velocity, right? Okay, if we were moving along the x-axis and velocity was negative, we interpreted that as, okay, we're moving to the left. But if we were moving to the left at a rate of, 10 miles an hour, the speed's still 10 miles an hour. So speed was the absolute value of velocity. And then we calculated total distance traveled by integrating speed because we wanted to always be counting more distance traveled. So, we didn't want to, start counting negatives and go backwards. That was for displacement or change in position or something like that. Calculating the final position based on the initial position. Okay, so we found total distance by integrating, between two time values, the absolute value of v. And just to remind you that integral was often pretty difficult to compute and was most likely to be something you were asked to do along with a calculator. Now, what I'm proposing today is that for two-dimensional motion, okay, we're going to be interested in, some kind of object that's moving in a plane, ant crawling along a sheet of paper or something like that, and the approach is going to be exactly the same. Okay, so our position function, you could define it with a pair of parametric equations. I'm going to use a vector. Because in 3 dimensions, it's much more likely that this will be framed as a vector equation. Okay, so I'm going to call it r of t equals, x of t and y of t. The velocity vector, that's velocity is still the derivative of position. And we can take the derivative of a vector-valued function by taking the derivative of each of its components. So that's x prime of t and y prime of t. Acceleration is going to be, you could look at it as the derivative of velocity, or the second derivative of position. It really doesn't matter. And either way, it's going to be the second derivative of x with respect to t and the second derivative of y with respect to t. For the speed is still the absolute value of velocity. Except now it's the absolute value of a velocity vector. Now, just kind of for now, I'm going to draw you this figure. Okay, we've got maybe this velocity vector v of t. Okay. This is x prime, right? How much x increased. And this is going to be y prime. And so we could find the length of v using the Pythagorean theorem. That the length of v would be the square root of x prime squared plus y prime squared. So that's how we'll calculate speed. And then when we go to calculate total distance traveled, well, we'll be integrating the speed. Okay, so we're going to be integrating the absolute value of velocity, which will turn out to be dx dt squared plus dy dt squared. And we'll integrate it over that time interval. Now, this might look familiar. You might be like, oh, last time I remember this, we took this same integral for arc length. And if you think about it, the total distance traveled along a parametric curve is going to be the same as arc length. Yeah, I think that's pretty much all you're going to need to know. The first example I've got for you is from your multiple choice packet, number 6. And I've got x is t squared minus 1, and y is t to the 4th minus 2t to the 3rd, and it wants the acceleration vector at the time where t equals 1. Well, I'll need x double prime and y double prime. Okay? A of 1 is going to be the vector given by x double prime of 1 and y double prime of 1. All right, so I need x double prime. First, I'm going to take x prime. That's going to be 2t. X double prime equals 2. Okay, well, that's regardless of what t is. X double prime is 2, so I know the acceleration vector is going to have its first component be 2. For y, I'm going to take the derivative of y, and I'm going to get 4t to the 3rd minus 6t squared. For the second derivative, I'll have 12t squared minus 12t. And then when I plug in 1, I'll get 12 minus 12 is 0. So I'm looking for the vector 2, 0. And when I flip through there, that looks like answer choice D. Next, I've got multiple choice question number 4 from your packet, and that's the particle moves along the curve y equals log x so that the x component has velocity given by x prime equals t plus 1 for t greater than or equal to 0. At time t equals 0, the particle is at point 1, 0. At time t equals 1, they want to know what's the location of the particle. Okay, so we're going to do some work on x, right? We've got an initial condition on x, we've got a rate of change of x, so we can recover information about the position. Okay. So I know that x of 1, just from the fundamental theorem of calculus, x of 1 is going to be equal to x of 0 plus the integral from 0 to 1 of x prime of t dt. All right, and then x of 0 is 1. And I'm going to integrate t plus 1 dt. So I'm going to say 1 plus 1/2 t squared plus t, as t ranges from 0 to 1. Okay, so 1 plus 1/2 plus 1 is 3/2, minus 0 plus 0 is 0. Okay, so I got 1 plus 3/2 is going to be 5/2. So I'll just go ahead and start in on my answer. I know that x component is going to be 5/2. And the y component is going to be, I don't know. Well, honestly, as far as the multiple choices go, you go and you look at these options, and C is the only one that has x coordinate 5/2, so you're done. You're choosing C. But I will show you how to, calculate the y coordinate. All right, now to find the y coordinate, I don't have information about the rate of change of y with respect to t. All right, so I can't just say y of 1 is 0 plus the integral from 0 to 1 of y prime. Okay, that's not going to work. What we can do instead is just say, well, I know that y is equal to log of x at all points along the path. Okay, so y of 1 is going to be the log of x of 1. So y is just the log of 5/2. Number 14 is, no, that's not number 14. It's number 12 is also similar, but I think there's another one in there, where it tells you, like, in terms of y equals f of x, what path the object's moving along, and then you kind of decide from there. All right. All right, now let's look at some free response questions. First, let's look at 2015 BC number 2. Okay, this is a calculator active question because it's the second question on the free response. They give you the velocity vector, they give you an initial position at t equals 1, and now they're just asking for what is the x coordinate at t equals 2. Okay, well, I know from the fundamental theorem of calculus, just like the other last question I did, x of 2 is equal to x of 1 plus the integral from 1 to 2 of x prime of t dt. Okay, now x prime is the x component of the velocity vector. So that's cosine of t squared is going to be my integrand. The problem is, that's not something that we can cook up an antiderivative for. Not going to happen. So, in the absence of that, that's where we bring out the calculator. We're going to use Math 9. Okay, so here it is. All right, so notice I've actually got my calculator in function mode. Parametric mode is great if you want to draw a picture of the graph of something, but as far as these free response question goes, I haven't seen any yet that require you to change your calculator into function mode. So what I'm going to do is I'm just going to calculate this integral. Okay, I'm going to use Math 9 to integrate from 1 up to 2. Okay, and it looks like I've forgotten my x of 1, which is 3. So I'm going to add that afterwards. Okay, so 2 of cosine of t squared. That's dt. And then I'm going to add 3. Okay, and so I get 2.557. And they ask, at what time does dx or dy dx equal 2? Now they were a little more verbose about it, but that's basically what they were asking. Is find me the t value where dy dx equals 2. The slope of the path is 2. What's the time at this point? All right. Well, basically this is going to be kind of a job for the calculator. Now they gave us the velocity vector, which is the derivative of x and the derivative of y. Okay, so we know dy dx is y prime over x prime. And we have y prime and x prime, like right here. So I'm going to just fill those in. Dy dx is e to the 0.5t divided by cosine of t squared. And we're interested in where dy dx equals 2. So as far as the calculator goes, I'm going to go in and I'm going to have it solve the equation e to the 0.5t divided by cosine of t squared equals 2, or that minus 2 equals 0. Now, I prefer to solve for the zeros when you're solving on the calculator. This one, it wouldn't make a big deal because it would, if you did the intersection technique, it would intersect at y equals 2. But if you're looking for the calculator to solve something where it equals anything bigger than 10 or more negative than negative 10, you're going to have to adjust the window, and that's just another thing that's taking up time. That would be a waste. So what we're going to do is we're going to bring in the calculator. So there it is. I just went into y equals in function mode, right? That's if you go into y equals in parametric mode and then go to calculate the zero or the intersection, you'll find that that's not an option. That those little commands have been removed. They are not available in parametric mode. So what you're going to do is use function mode. And then we go in, we're going to graph the thing. Now, in the fine print of the statement of the problem, they said t was greater than 0. So I am only going to focus on t being between 0 and, let's just say, 5. Oh, there it is. Oh, and look, that's interesting. Okay, so it's only going to happen here. All right, so we're going to calculate a 0. It looks like it's kind of around 1, so I'll say it's between 0 and 2. So I'll just tell it to use left bound 0, right bound 2, give it a guess of 1, and then there we have it. Thing is, that's too far away for me to read. Can someone read that out to me?
0.840.
Okay, so 840. All right. equals 0.840. And that's, how we're solving that. Now, really important to mention is that as far as the scoring guidelines go on the free response section, if you use the calculator to solve an equation, you absolutely have to write the equation that you're solving. Okay? If you just come up with a t-value, you are liable to not get as much credit as you should. You need to say, okay, this, has solution t equals 0.840. That's something that people in my class have forgotten in the past. Part C asks, at what time is the speed equal to 3? Okay, well, I know that speed... Speed is the square root of dx dt squared plus dy dt squared. So I'm over here, I'm going to say this is cosine squared of t squared plus e to the 0.5 t squared. And, maybe you know what that is, but if we're going to put this into the calculator anyway, no sense in risking algebra error. So we want to know where the speed is equal to 3. So again, for the reader, I'm going to write the equation whose solution I'm going to find using the calculator. Okay, that should be enough. Cosine squared of t squared plus e to the 0.5 t squared equals 3, or minus 3 equals 0. And then I bring in the calculator. And again, I just plug that into y equals in function mode, because that'll help us. We're still only interested in t being greater than or equal to 0, so it's still on the same window setting from before, but I would want to make sure that my independent variable was, just greater than 0, and not too much that we'd have a hard time locating the actual crossing point. We go and it's going to go to the table. Just give me the graph. There we go. All right, and that's going to be what we look for. So we go to calculate. That's where all the good stuff is. We want the 0. Looks like it's bigger than 2 and smaller than 3, but I'll just say, a left bound of 1, a right bound of 4. Give it any guess. There's only 1. And we get ourselves a t-value. But I can't see, that's too far. Will somebody read it for me? 2.195 or 2.196. Okay, just to remind you, okay, on the free response, we're looking for 3 decimals, and you can either round it, which is what I do 90% of the time, or you can just read off the first 3 decimals you see. You can trunc it. No judgment. The readers are ready for that eventuality. And then part D is asking for the total distance traveled by the particle on the time interval 0 to 1. So I know that distance is the integral of speed. So that's the integral of, it's just 0 to 1 of this square root. And I kind of wish I'd saved that square root, but it's all right. Cosine squared of t squared plus e to the 0.5 t squared. Square rooted. Integrate with respect to t. All right. Now, I'm going to bring in the calculator. And the convenient thing is I already have this square root typed in here. So, no, I can't do that. Okay, so I'm going to have to click over there. I'm going to get rid of the minus 3, though. Right? Because I don't want to integrate that. But then I'm going to call on y1 when I go to do this integral. Okay, rather than typing this all over again. Okay, so I quit. I'm going to integrate using Math 9 from 0 up to 1 of, okay, now I need to call on y1. Okay, you go to variables, y variables. Okay, we are in function mode despite this being a parametric problem. Okay, single variable integration. Call on y1 with respect to t, which we were actually using the x button for. And then we let it think for a while, and we get 1.595, or 594. Or 1.595. Whatever you want. Okay, that was 2015 BC number 2. Now let's go ahead and look farther, deeper into that packet, and look at like a really old one or something.
All right, so here's one from 1987. It was number 5 on the BC exam. We got x given by sine t and y given by cosine of 2t, where t is running over the interval 0 to 2 pi. First, they're asking for the velocity vector at time t. Okay, that's really easy. We're just going to take the derivative of x, the derivative of y, write it as a vector. Part B is asking you to find the times when the particle's at rest. So we need to know when the velocity vector is the 0 vector. So I need the velocity vector, which was cosine t and negative sine of 2t, to equal the vector 0, 0. Would be it being at rest. So I need cosine t equaling 0, bless you, at the same time that negative sine of 2t is equal to 0. And you might be thinking, I don't think that's going to happen, but if you just carry it out, I think it will. Cosine is equal to 0, and in the statement of the problem, they said 0 to 2 pi only, so this is really nice. It's the same pi over 2, 3 pi over 2, and okay, if sine is equal to 0, we know that's 0, pi, and 2 pi. Okay, so that means that 2t is equal to 0, pi, 2 pi. Now, you may remember from pre-cal that you might need to consider all the way up to 4 pi because we have twice as much here. So I'm going to go with 3 pi and 4 pi. Meaning that the places where negative sine of 2t equals 0 is 0 divided by 2, pi divided by 2, 2 pi divided by 2, 3 pi divided by 2, and 4 pi divided by 2. And we're just looking for places where both of these are equal to 0. So I'm seeing pi over 2. Seeing 3 pi over 2. Okay, so the particle's at rest at t equals pi over 2 and t equals 3 pi over 2. Part C asks you to write an equation for the path of the particle in terms of x and y that does not involve trigonometric functions, which is basically a question asking you to eliminate the parameter and use trig identities. And in my opinion, that is just not the type of thing that they would ask you to do these days. It's something that might have been something eligible in 1987. I'm sure, I guess, technically it is eligible for testing now, but that's, if you look at the more recent items, you're not seeing anything like that. And speaking of that, Part D was asking you to sketch the path of the particle in a grid that they provided in the answer booklet, and they don't do that anymore either because so many people are taking the exam now that the readers just don't have time to grade all those graphs. So that's really not something they're going to have to worry about.